Hi all. Today we discuss an example first. Let This is 4.1 for example. Let star be defined on Q plus. Q plus means set of all positive rational numbers by A star B is equal to A into B divided by 2. So this is the definition of this map. So this form a binary operation on Q plus, because if we choose any two positive rational numbers A and B, then A star B by 2 is also a positive rational number. So this defines a binary operation on Q plus. Now let's verify the associativity property of the star by evaluating A star B star C. This is in fact AB by 2, that is A star B star C, which is equal to A B C divided by 4. In a similar fashion, you can get A star B star C. You can evaluate this by A star B star C is equal to BC by 2. So this is same as BC by 2. This is same as ABC by 4. From this you can say that the star is associative. This binary operation is associative. Now let's verify the existence of the identity. So to find an element, the identity is defined as E. What is the property of this identity? A star E should be A, that is equal to E star A for all A. Okay, so we have to find out an element, this A E, such that E satisfies this condition. Okay, so by definition, A star E is equal to, we start with the first equation. A star E is equal to A implies, what is A star E? By definition, that is A E by 2 equal to A. Okay, this implies, since these are all real numbers and rational numbers, we can solve this by A E equal to 2 times A. This implies, from this you can write E is equal to 2A by A. Since this A comes from Q plus, this A is non-zero, then this E takes the form E is equal to 2. Okay, if an identity exists, then that must be 2. Let's verify this 2 is an element of Q plus. Obviously it is an element of Q plus. So we can say that this 2 is the identity element of Q plus. Okay, now we can verify the existence of inverse by evaluating the equation. For existence for the inverse of A, we denote A prime such that A star A prime is equal to identity, which is nothing but 2, and we have to solve this one. Okay, so this implies A star by 2, that is the definition of A star A prime. So this is A prime by 2, that is equal to 2 itself, because E is equal to 2. So this implies A prime is equal to this 4. This implies A prime will be 4 by A. Since this A is again an element of Q plus, 4 by A defined for every A belongs to Q plus. So this implies A prime is the inverse of this A. Okay, so for every A we have the inverse. So from these 3 statements, we can say that this is the first axiom of the group, and this is the second axiom, and this is the third axiom. Therefore this form a group. Okay, now let's verify the commutative property as well. If we start with A star B, that is equal to AB by 2. Since these numbers are A and B are real numbers, you can write it as BA by 2, that is equal to B star A by this definition. So this implies star is also commutative. Okay, star is commutative as well. Therefore we can say that this Q plus along with this binary operation star is an abelian group. Is an abelian group. Now we will prove a theorem. This is due to some group, the property of the axioms of the group. If G is a group with binary operation star, then left and right cancellation laws hold in G. By left cancellation law, we mean that A star B is equal to A star C implies B is equal to C. And right cancellation law means B star A is equal to C star A, if this is A, then we can get a B equal to C from this equation. So these two properties are called left and right cancellation law respectively. So we will prove this theorem by taking the first A star B. If you assume A star B is equal to A star C, since this is a group, then you can apply this A for every A belongs to that group. There exists the inverse for A, so we denote that as A prime. So we apply A prime on both LHS and RHS. We can get A prime star A star B equal to A prime star A star C. Okay, so here we apply the inverse of A, which is so A is A prime. We apply this A prime on both sides. Okay, so this implies since this star is associative in group G, then we can associate A prime and A first. Okay, then star B. Similarly, you can associate this A prime A first and then C using the associative property, associativity of star. This implies we know that A prime star A is identity element because these are the inverses. So E star B is equal to, again this is identity element, so E star C. This E is the identity element of star. Okay, so this implies E star B is equal to B, since E is identity. E star C is equal to C. So this proves the left cancellation law. Okay, similarly you can easily prove this right cancellation law. So I left it as an exercise to prove the right cancellation law. The similar fashion you can easily prove the right cancellation law. Prove the right cancellation law. Okay. As a consequence of the previous theorem, we can prove this interesting result on groups. If we consider any two elements A and B in that group and construct two equations, linear equations, A star x equal to B. This is the linear equation in the unknown x, and y star A is equal to B, that is another linear equation in the unknown y. Then these two equations should have only a unique solution in this group. So that is this theorem. That means when you consider this linear equation, it has exactly one solution. So that is the first thing. So that is due to the cancellation laws. So first of all, we will prove that there is a solution in this group G. So for that we consider A belongs to G implies we know that A prime, that is the inverse, belongs to G such that A star A prime which is equal to A prime star A which is equal to the identity element. Okay, now you take this equation, or if you take x equal to this A prime B, this A prime star B, that is the inverse of A prime is the inverse of A, we can get A star x, that is equal to A star. We put x equal to A prime star B. Then we can associate these first two elements, A star A prime star B, which is equal to E star B which is equal to B. It shows that if you put X equal to this one, this is an element of G obviously, because A prime and B are elements of G and G is a group, then you can get A star X equal to B. So this will be the solution of this linear equation. Now you can prove that if there exists two solutions, then they must be the same. That means it will not have more than one solution. That is the next thing. So first of all, we consider suppose we consider there are two solutions for this linear equation A star X equal to B. Then we let it be x1 and x2 be two solutions of A star X equal to B. Then we can say that A star x1 equal to B, and then we have A star x1 equal to B, and A star x2 is also B. Okay, from these two equations we can say that A star x1 equal to A star x2. By cancellation law, by left cancellation law, this implies x1 equal to x2, which shows that these two solutions are the same. Okay, now we can say that this A star X equal to B has exactly one solution. Okay, the similar fashion you can prove Y star A equal to B has only one solution. Okay, now we will prove theorem 4.17. The statement of this theorem is in a group G with binary operation star, there is only one element E such that E star X equal to X star is equal to X for all X belongs to G, and likewise for each A belongs to G, there is only one element A prime such that A prime star A is equal to A star A prime is equal to E. Okay, that means this equation shows that E is the identity element of the group. So the statement, the meaning of the statement is the identity element of the group is unique. We already proved that the identity element of the binary structure is always unique. That is that we have proved in theorem 3.13. So the first part is so trivial because G is also a binary structure. Then if there exists an element E in that structure, then that will be unique. So we are not going to prove that again. And but we will prove this result, the existence of the so the uniqueness of the inverse in this group is unique. That we will prove in this theorem. Okay, so please refer 3.13 for the proof of the first part. For the proof of first statement or first part, and the second part will be proved here. So we have assumed that there are suppose there are two elements satisfying the same condition. Suppose there are A prime and A double prime such that A prime star A equal to A star A prime is equal to E, and A double prime star A is equal to A star A double prime, which is also E. Suppose there exists two such members of G, and we can say that from these two equations, A prime star A is equal to E, and A double prime A star is also E. So from these two equations you can write A prime star A is the same as A double prime star A. Okay, so this implies from the right cancellation law, these equality implies that A prime is equal to A double prime. Okay, which shows that the inverses of each of the element A are unique. Okay, as a corollary of 4.17, we can prove this result. 4.18, let G be a group. For all A comma B belongs to G, we have A star B is equal to the inverse of B star inverse of A, B prime and A prime. So this is we already proved that the inverse of A is always, if A belongs to G, then inverse of that element is always unique. Then we can say that this A star B is an element of that group G, then inverse of A star B, and that is denoted by A star B prime. Okay, so this A star B prime will be unique element in group G. We will prove that that element is this one. To prove this result, we have to prove that the inverse of A star B is a B prime and A prime, B prime star A prime. So we will prove that these two, if we consider this as an element B prime star A prime, and we consider this A star B is an element of G, then if we operate that element with this is equal to identity. Okay, that means by associative property we can write it as A star. We can associate the first two element the second and third element B star B prime star A prime. Then we can replace the element in the bracket by E. This is A star E star this A prime, because this is the identity element. From this you can write A star E is equal, or you can E star A prime is equal to A prime itself. So this is A star A prime, that is equal to E, which shows that if you operate this element with this, we can get identity element. So this can be considered as the inverse of this element. That is nothing but the statement A star B prime is equal to B prime star A prime. Okay, which shows that this is the only inverse because of theorem 4.17. This is the only inverse of A star B in G. Okay, so this is the way we evaluate inverse of some element in inverse of some A star B in group G. Now we have some remarks on these definitions and properties of group G. For a G we have three axioms. We have the group is always a binary structure with binary operation star. Then if this the structure satisfies three axioms, that is, the first one is the associativity, and second one is the existence of identity element, and third one is the existence of inverses for each of the elements, this G. And if we have G, if we have a binary structure G star along with G1, okay, then this is called a groupoid or a quasi group. We call this structure as a quasi group. Okay, and this algebraic structure with the first two axioms. This is a binary structure which satisfies G1 and G2. We call this as semi-group, and this binary structure with this algebraic structure with these the first two axioms. The group, the binary structure G star itself is called the quasi group. This is the quasi group, and we consider this algebraic structure or the quasi group along with G1 is called semi group. Therefore, G is that means G is a set and star is a binary operation on G, and that binary operation is associative. Then that is called semi group, and we have the first two axioms, that is G1 is associativity, G2 is the existence of identity. Okay, so if you are not bothered about the existence of the inverse, then this structure is called monoid. Okay, obviously if G with all three axioms is called the group. Okay, so if we have a group G star, then if we redundant the axioms, some of these axioms, we can get the other algebraic structures called quasi group, semi group, and monoid. Okay, semi group means this quasi group means G along with a binary operation, and semi group is G along with the binary operation which is associative. Okay, and monoid is this group G along with the binary operation along with the axioms, the associativity and existence of the identity element only. Okay, now that is called monoid. Then you can get the group. So using these facts you can get some substructures, or if you weaken the conditions axioms of group, then you will get these structures called quasi group, semi group, monoid. Now plus we are not going to elaborate on these structures. We just give the names of these three structures. Okay, and another remark is, if you consider the identity element, we know that A star E is equal to E star A for all, A star E is equal to A for all A belongs to this G. Then we call this is the left identity, or the left identity element, right identity element of G, because we apply G on the right side. Okay, and if we have E star A is equal to A for all A belongs to G, then we call this E as the element satisfying this condition is called the left identity element. So if we, for identity element, we will expect these two conditions. Okay, if these two conditions hold, then we can say that E is the identity element of that group. Okay, so if you are given this condition only, you can prove that if this is true, then you can prove that this is also true in a group. Okay, so therefore we are not going to consider all these two equations always in the following theorems. We will prove only this one of these conditions. Okay, either you can prove the right identity is there, or you can prove the left identity is there. That is enough to get the identity element of the group. Okay, similarly you can use the idea of left inverse and right inverse. So some remarks are given in your textbook after this corollary 4.18. So please go through it. I hope all of you have the textbook right now. Otherwise, please inform me. I will give you the PDF of this textbook. Another thing you have to remember is, likewise we have discussed in the algebraic binary operation table, or in the algebraic structure binary operation table, we can discuss the group table in or corresponding to this group. If we have a group G with binary operation star, and if it contains three elements, then suppose obviously G should be a non-empty set. Okay, this never be empty. Then G is always non-empty, so it should contain at least one. So if G contains at least one element, then one can expect the first element is the identity element, because G should contain exactly one identity element. So that identity element is in this G. Then if G, this is the simplest group we can construct. Okay, so corresponding to this group, you can construct the binary operation table as if it contains only the identity element, then we have E star E is equal to E. Then this is the simplest group in this structure. Okay, and if G contains two elements, then we can expect first one is E, and we have another element. Okay, then what will be the binary binary operation table or group table of this group? Since this contains two elements, we can write this is first one is E and second one is A. This is E and this is A. And suppose in that group we can get E star E is equal to E and E star A. Since this E is identity, E star A is equal to A itself. Similarly, A star E is also A. Now we have AA. Okay, so what will be the element AA? So this A star A has two possibilities. Either it will be A or E, or it will be A. These are the only two elements of that group. So A star A can be one of these elements in this group G, E comma A. So if A star A is equal to this E, what is the meaning of that? A star or A star A is equal to A. This implies A star A is equal to, this A can be replaced as A star E as well, because A star E is equal to A. By left cancellation law, this implies A equal to E, so which is a contradiction. We assume that this group contains two elements, E and A, so this these two quantities never be equal, so this never happens. So what is the other possibility? AA should be, this is not possible, because AA is equal to A implies A equal to E, which is a contradiction, and the only remaining possibility is A star A is equal to E, so we can fill it with E. Okay, so this is the only possible group structure with two elements. Okay, that means if a group contains two elements, then the only possible binary operation is this one. Okay, you cannot define more than one binary operation on that algebraic structure which gives the group. Okay, now if we have three elements, we named it as E, that is the identity element A and B. Okay, then what is the possible groups or group structures in this regard? Then if we have a star here, this is E A B, E A B, then since this E is the identity element, E star E will give E, E star A is A, E star B is equal to B. Similarly, A star A star E is A, B star E is B. Okay, so these are the possibilities. In order to fill up in this box, we need to verify that A star A cannot be this A star A has three possibilities. Either it will be E, and the other possibility is A, and we have B. Okay, so these are the only possibilities for A star A. Okay, but A star A never be A. We can easily rule out this possibility because of the same reason we have discussed earlier. If A star A is equal to A, that implies A will be this E, so that is a contradiction. That means if this happens, then we can get E, then that is a contradiction. So we ruled out this one. And if this A star A is equal to A star A is equal to this E, then this is one question. There are two possibilities. Either you can fill E or B in this box. Then if A star A is equal to E, then what will you assign for this A star B? Okay, if this is E, then we need to fill an element here that has only three possibilities. Again, E, this B, A, B. So these are the only possibility in this box. If you fill up it with E, then what will you be fill up it with this box? So from this you can say that A star B is equal to A implies this by cancellation law we have discussed earlier, we can get B is equal to identity, which is a contradiction. So we ruled out this possibility. A star B is equal to B, then you can get A is identity. So this is also a contradiction because A never be an identity. So we can rule out this possibility. This is because A star B is equal to A, that implies A star B is equal to this A star E, because this A can be replaced by E. By left cancellation law you can get B is equal to E. That is what you have given here. So that is a contradiction. In the similar fashion you can get A equal to E in this. If we assign A star B is equal to B, then we have A is equal to E, which is also a contradiction. So the only possibility for this A star B is equal to E. Okay, so we need to fill this box. The only possibility is E, and if we fill E here, then what happens? A star A is equal to E, that is equal to A star B, because A star B is the only possibility for A star B is E. Okay, and if we fill this box with E, then this happens. A star A is equal to E, that is same as A star B, which implies by left cancellation law we can get A equal to B, so which is a contradiction as well. Now if we fill A star A is equal to E, then that is again a contradiction, so we can rule out this as well. Okay, this implies A equal to B, which is also a contradiction. Then the only possibilities for A star A is B, so we can replace this quantity by B. Okay, so this is B. Now you can easily fill up the other things. This B star A has the three possibilities, A, B, E, but we know that this is not possible. We already discussed that. If we have wrote out this one, then the only possibility for B star A is equal to E. Okay, otherwise you can think of this A star B. This A star B is equal to E. That means B is the inverse of A. So we can get A is the inverse of B. So B star A will always be identity element. Okay, so the only possibility B star B is equal to E. Okay, you can easily verify that. The other B star B will have three possibility, E, A, B. Then you can easily rule out using these ideas, E and B again. Okay, now you can get only one possibility. So if you have three elements in a group, then we can get only one possible group table for that group. Okay, so if you have four elements, then there will be more than one possibilities for a group table. Okay, so if the group contains more than three elements, then there are different possibilities for this group table, and we can expect the different group structures with those four elements. But these discussions say that there are only one possibility for a group with one element, and only one possibility for a group with two elements, and there is only one possibility for a group with three elements as well. Okay, in the next class we will discuss the other section, section 5, the subgroups of a group.